So my talk is about privacy region, which is another way of looking at differential privacy using two-dimensional nice pictures. And I'm going to tell you how to go from one to the other and how to use this notion to prove some results that are interesting and improves upon the state of the art. So the outline is going to be the following. I'll tell you what these regions mean. I didn't tell you yet. But this allows to do things like if you have, let's say, two different mechanisms. In this case, this is a region corresponding to the famous Laplacian mechanism. This is something else. For example, if you have two different mechanisms, let's say both epsilon differentially private, then there are many different mechanisms, and how can you say one is better than the others, or one is more private or less private than others? And we give a formal notion of comparing such privacy mechanisms. And this also gives us a operation. For example, if you have another privacy mechanism, I didn't explain what the pictures mean yet. It'll be clear soon. But if you have two different mechanisms, then let's say you do composition, and what is the resulting mechanism look like? Meaning, let's say you access a database, one using maybe Gaussian mechanism, the other using Laplacian mechanism. You access it twice. Now it's less private than any of one of them, but how much and how can we formally talk about this? And we give a computational tool for composing, not just two, but as many privacy mechanisms as you want, and give a formal computational tool for outputting the resulting privacy guarantee using the representation that we propose. And given this tool, what you can do is, well, this is nice, but what is it good for? So I'm going to show you that it's good for a couple of applications, and the ongoing theme will be that the recipe will be that we look at interesting problems that have been studied by the privacy community, and for each one of them, we're going to use our tool to come up with a similar result, but which is oftentimes tighter and holds for more general cases, meaning we are less restrictive in the assumptions, and oftentimes the proof is much, much simpler. And that's our goal for 4 examples. One is composition theorem that Lalita talked about, but in a very different context. And multi-party computation is another one, local differential privacy, and selling privacy or pricing the private data. And these references I put are by no means any first papers on dealing with privacy for such examples or topics, but the ones are most relevant to the result that we're going to talk about. Right. So let's start. So what does privacy mean? So I'll start with a very simple example by Warner. So the question he wanted to ask is maybe, have you ever used illegal drugs to many people and get a statistics on this? Maybe he wanted to know how many people among all the population are using drugs. But because it's a sensitive question, what he told them to do to preserve privacy is that, well, he gave them a coin, asked them to flip it, and if it's a head, then you always say yes, and if it's a tail, then you answer truthfully. And this preserves privacy on the one side because, well, if say you didn't use it, then you're happy to say you didn't use it. But if you used it, you want some deniability, some plausible deniability that there are other people who didn't use it, who said they used it. Or it's the coin and not me. So this was called randomized response. And the way we're going to look at it is that, well, look at this simple privatization scheme. There are only 2 alphabet in data, whether you use it or not, and the outcome is whether you use it or not, so it's 2 by 2. So given that, let's say your null hypothesis is you didn't use any drugs, then with probability half, you say yes, and with probability half, you say no. And if you are the kind of person you use the drugs, then you say yes all the time, right? So that's representing the coin flip as a probability transition matrix. And the way we want to view it is that, well, let's say you get one data from a person and you want to do hypothesis testing on whether that person really used the drugs or not. And we're plotting all possible combinations of probability of false alarm and probability of misdetection. So for different rejection sets, in this case, the output is only 2. So there are only really 3 points that are interesting. This point, and this point. All the others are just the interpolation of those by using randomization. But what's happening is that, well, whatever you do, you are only able to achieve probability of error, in this case, on one side or the other, the combination that's in this region. So you get this triangle region. So you can think of it as symmetric, because I'm not drawing anything above, because it's everything, you could flip the definition and everything is symmetric. So we are interested in this below 45-degree line. I'm just plotting that. And what's shown in gray in this triangular region is the whole combination of type 1 error and type 2 error that you can achieve based on this private mechanism. Right? And by changing the bias of this coin, for example, you use a bias coin with bias P, then you can make this scheme more private or less private, obviously. And in this example, you choose a coin with bias P, then you achieve this darker gray region, meaning that the region is smaller, probability of error is larger, so this is more private. Okay. More private than the one I told you before. More private are ones that you get more error, that are more difficult to write. So the smaller region means your error is larger, so you are more private. Okay. So here, I want you to explain a little bit more here, so please.
No, go ahead.
Right, so what I have to explain is a couple of things. So here, I'm giving you a scheme parameterized, a family of schemes parameterized by the bias in the coin, which is P. And changing from P to 0 to 1, you have this family of schemes which are less private and more private. And you can represent it in a two-dimensional diagram like this. And then the larger P, smaller region, means you're more private. Okay. And the other thing is that, well, did you have a question before I go to the next?
I'm just trying to understand what you're plotting.
What I'm plotting, okay, maybe I should be a little bit slower in this.
What are the axes?
Right, so what I'm plotting is that, well, let's say given the output, you flip the coin and told me the answer. Given the output, let's say I always say that you're...
The equation up top is the label on the axis.
Yeah, label on the axis. Sorry about that, yeah. So I was a little bit quick on this. This axis is probability false alarm, which is defined as probability that output is in the rejection set for whatever choice of rejection set. So different set of rejection sets give you different points in this region. And I'm plotting everything. Right. So one is one type of error based on H null, which is you're not using drugs, and which is the other one. Two types. Right. This only depends on this. This is 1-to-1 going from the region to a conditional probability. And I'm looking at this family of mechanisms.
Wait, did you say it's 1-to-1 going from the region?
Not 1-to-1. Given this, I can plot this.
Right.
Given this, there could be many. That's precise. And I'm looking at a family of mechanisms. And one thing is that, well, this gives you a way of comparing, at least in this context, but in general context, they'll make it clear, comparing two mechanisms. And another thing is that in this example, let's say I collected data from all of you using a coin with no bias, so it's half-half. And then later I went home and I figured out that, well, the data should have been more private than what I collected. In that case, what I can do is I can just look at the table of the data I got from you, and for each one I can flip a different coin with appropriately chosen bias, such that the resulting sanitized database is one that I shoot for the right P, for example, if your region is smaller, meaning P is larger than you're shooting for. Okay? So what I want to say is that, well, given a mechanism, output of a mechanism that's let's say less private. If you wanted a more private output, then there is a statistical process that takes the output of the less private one and adds more randomness to produce the output of the more private one. In this family of mechanism, at least in this example, those two are true. And that's true in general, as we'll show.
So it's true in general that at any time the this region for one mechanism is contained in the region of another
exactly.
mechanism, then
That's what I'm gonna. That's the main result that I'm gonna show in the first maybe quarter of the talk. But I just wanted to illustrate this to get you familiar with the region concept and how it corresponds to maybe a concrete mechanism. So this was a toy example, but everything I said about this toy example holds in general, and that's our main result. Well, let's go to something a bit more complex. So differential privacy, how is this related to differential privacy? So I'm not going to go to the definition, I'm just going to state it. And this is an example of two databases that are neighbors. So I'm missing just a data about me on this database. Everything else is the same. So differential privacy ensures that probability of getting the output from one database is bounded by e to the epsilon times the probability of the other one. It's one way to achieve this. In this particular example, let's say you're counting how many people are above 30. Then your data is integer, sensitivity is 1, so you can add Laplacian, and it ensures that for any set S, for example this, the ratio is met. It's well known. So what I want to do is, well, how does this correspond to, and you can do this for epsilon delta differential privacy, where you're allowed to say truth with delta probability, and 1 minus delta, you use your favorite epsilon differential privacy scheme. Right, so how does it relate to the privacy region is what I call the figures that you're going to see. Well, let's say for the first quarter of this talk, I'm going to assume that the whole world is only two databases. So there's only D0 and D1. As you get more, and if you get complicated neighborhoods, things get hairier, but we don't have to get there yet. So in the whole world, there are only two databases, D0 and D1. One is our null hypothesis, and the other is the alternate hypothesis. And for if you are using a, let's say, Laplacian mechanism, then your privacy region is going to look something like this, nice curve. And depending on how you choose your rejection set, you're traversing different points on the boundary. Like for different choices, you get different points, and putting them all together, you get this region. And one observation, the first observation is that, well, differential privacy can be interpreted as a particular linear constraint on this privacy region, meaning that, well, that's the differential privacy constraint for epsilon delta. And if you interpret your S as the rejection set S without loss of generality, then you get this particular inequalities, two of them, just by changing the notations on your false alarm error and misdetection error, which gives you two half spaces, intersect them, and you get this nice triangular region. And this is delta, and the slope has to do with epsilon, but I won't go into the details of what each values are. And let's call it R of epsilon delta, which corresponds to the intersection of two half spaces defined by epsilon delta differential privacy. And one thing that we know is that, well, if your mechanism is epsilon delta differential private, mechanism Q, then they satisfy these two equations. So they better be inside, like this one. And the other is true. If for any pair of neighboring databases, if your mechanism gives you a region that's inside, then it's also epsilon delta differentially private. So that's how formally differential privacy and this region notion is related, which it's not our observation, it has been observed by Wasserman and Zhu earlier. And what do we use this for? We're going to use this to come up with a data processing inequality that's going to be very, very useful later. What it means is that, well, there are going to be two sides to this data processing inequality. One side is clear, that's why I call it observation, which is that, well, think about a way of accessing our database through a mechanism Q1, and then somebody access the output of Q1 and adds more randomness, more private data, and call it Q2. Okay? Then clearly, Q1 is less private, Q2 is more private because you added more noise, and there's no ambiguity on this. And what it implies for the region is that if that's true, if that particular Markov chain holds, or particular dominance holds, in the sense that I just explained, then the region of the more private one has to be inside the region of the less private one. And this follows from simple, almost simple logic. And that's the trivial way of data processing inequality. But what's somewhat surprising and not clear is that the other way is also true, meaning that, well, again, I'm focusing on the world where there are only two databases. If you talk about multiple, things get hairier, and I'll get to that. So there are only two databases, D0 and D1, and I have Q1 and Q2. And they are not related. There's no relationship, meaning there's no joint distribution among them. But you draw the privacy region for each of them, and one of them happens to be inside the other. Then what is true is that converse to the data processing inequality also holds, meaning if the region is contained, then you can come up with a particular mapping that maps the output of the less private one and produces the output that's statistically equivalent to the output of the more private one. So you can talk about it in terms of Markov chain or in terms of transforming the output of one and getting the other. So that's the non-trivial data processing, or converse to the data processing inequality that we're interested in. And we proved it ourselves, but ends up that it's well known since 50s. Not in this context, but in more or less the same context.
What was it called by Blackwell?
It was called comparison theorem because it's comparing two statistical experiments. And his results are more general than just the two database case, but
Maybe some more discussion required on the cost or any general risk. Is it true for any general risk?
Well, it's true on the context of what I said. In the general context, things are get a little bit, you have to be more careful. For example, if there are not just two, but like three experiments or three databases in this context. And so the region gets so any projection of the region is included on the other, then it's true and things get hairier. You can easily see. So you have to look at all infinite projections. If they're all contained, then this holds, but that doesn't mean anything for us in our context.
Something like if all Bayesian tests would be
Exactly.
So think this direction, you need to know D1 and D2. This is only one in order to...
Right, so this is, so right now it doesn't make much sense in general databases, but this is what we're going to use to talk about a lot of the interesting problems. So this is for particular D0 and D1. Let's say you just one neighborhood and you're just interested in that. Mm-hmm. So that's the most limiting part of this theorem, but that's the truth. So related to your impossibility of universal mechanism for more than three, I'll get to that and how it kind of intuitively gives similar ideas. All right. And one thing in particular that's going to be interesting is that, well, this gives us something called dominant mechanism for epsilon 0 or epsilon delta differential privacy. And it looks like this. It's appeared in many times in different contexts. And it's the following. With delta, you say the truth. So A means your database is D0 because it can never come from D1. D means your database is D1. You tell the truth. And with 1 minus delta, you do randomized response, coin flip. That's tailored so that it's epsilon differential private within them. And the reason it achieves will be exactly this pentagon that I said is our epsilon delta. So what it means now that we know converse to data processing inequality is that any epsilon delta differential privacy operating on these two databases should be inside by definition and can be simulated from the output of this particular one. And that's why I call it dominant strategy or dominant mechanism. And this is going to play a crucial role improving important results.
I have a question, and feel free to like postpone it or take it offline. But if I wanted to ask, suppose I start with some prior on the two data sets.
Yes.
And I want to think about like what kind of posterior distributions can arise for various types of outputs.
Yes. So this is completely.
By what this region is?
So the region is independent of the prior, meaning it assumes there is no prior.
There's no prior.
Right. It only depends on the conditional.
If you do try to cast this.
Had you done it, it will be like projecting it on a particular line.
Priors are the tangents to this region.
Right.
It captures all the priors. The region captures, when you talk about prior, I think you are talking about a particular tangent with a slope in that region. So it's more general.
So prior will be a particular mixture of these two, usually. So it's either projection or a tangent that you will be looking at depending on the prior. And what does it mean in terms of differential privacy? I do not know, because the differential itself is not doesn't take prior into account.
Okay, I don't want to. All right, I can.
I think it's going to be a longer discussion than I think for now. Okay, so let's take it, and I'll tell you a bit more about this. Maybe it's related to what you're thinking. So one thing that's related will be, let's say we're doing counting queries, for example. Okay, query output is an integer. Neighborhood is whatever is within 1. It should be less than equal to, okay, 1. And neighborhood graph is a line in this case, right? If you look at the output, that's an integer, then anyone who's next to it is a neighbor in the differential privacy definition sense. And in this case, we can think about adding geometric noise, which will be, for example, if it's 31, so adding geometric noise, and 32 with appropriately chosen variance so that epsilon 0 differential privacy in this case is met. And the interesting thing is that this is an example of this. I'm just giving you an example of a real problem with a real mechanism, what it looks like. The corresponding mechanism for any pair of privacy region for any pair of neighboring database, neighboring query outputs is going to be exactly the triangle region, which is exactly R of epsilon, which means that no other algorithm can have a bigger region. And if you focus on particular 2 neighbors, then this is optimal, meaning any other mechanism, epsilon differential private mechanism, can be simulated from this. But the simulation might depending on the neighborhood. So this is not universal in itself, but certain universality results has been known from 2012 or 2010. The first draft by Ghosh, Roughgarden, and Sundararajan. And that's because they look at particular utility, not in this general dominant sense, but if you look at utility and look at expected, minimizing expected loss with priors in a Bayesian setting, then you can talk about universal dominance of this mechanism. But you can intuitively see why that's a good idea in this case. But in general, for any general settings, perhaps your neighborhood is a, let's say, triangle, meaning you have 3 outputs, 0, 1, 2, and they're all neighborhoods. Whatever the query and whatever the database is, they all can change by changing one entry in the database. Then what you want to achieve a triangle region is that all the outputs given the actual database or query output that are neighboring to be equal to epsilon. You want the ratio to be e to the epsilon on all of them. In that case, you get the triangle that we want. And you can see it's impossible for 0, 1, 2 and all of them to satisfy this. It's easy to see. So that's another intuitive reason why having a dominant mechanism that's universal for neighborhood that's not binary, when your database is more than just 2 kinds, it's difficult. And this, again, notion has been made precise in a different context where utility is measured in a Bayesian setting by Brenner and Sim, 2010.
Question, what is a universal dominant?
Universal dominant mechanism would be that, well, if your database is just 2, okay, so let's say there's binary data, that's your private data, and I ask for any query on it using epsilon 0 differential privacy, then you can give me a randomized response, and whatever other epsilon 0 differential private mechanism anyone wants, I can simulate it from your output of randomized response. So there's one mechanism which you need to use over the queries, over the, for example, yeah.
So over all those, but I thought you were saying that there is a boundary, but you're saying that we may not be able to attain that boundary.
Right. So for any pair, you can achieve it, but for the mechanism that's using that's dominant for that pair, would be impossible to for the other 2 pair. For example, in this example, there are 3 pairs that you need to consider. For one pair, you can make it dominant, but given that you use that mechanism, the other cannot be made dominant. Because the ratio, what about output units? Ratio between this and this has to be e to the epsilon. One has to be bigger. The other also has to be e to the epsilon, and this also being e to the epsilon, that's impossible just by construction.
So what that means is that for a neighborhood like that, you cannot actually have any privacy mechanism?
So what it means is that it depends on the utility that you're going to look at. So the dominance that we're talking about is complete dominance. You can simulate the whole thing, which is quite a lot to ask for. So in those other settings, what you do is, well, it's impossible to completely dominate for all utilities and for everything. But what you can do is, instead of requiring this to be epsilon, you require that to be epsilon or 0. And look at all family of mechanisms where it's epsilon or 0. This is what we came up with, which we call staircase mechanisms, because it kind of looks like a staircase. And those are known to be optimal for particular utility that you're looking at. So based on what utility you're going to look at, there will be a dominant mechanism, and that's from one of these family of mechanisms in some contexts. I'm not saying it's always, but in some contexts that I'll talk about later.
So can you go back one slide to the, yeah. So using these regions, is there a way to get, say, a universally optimal mechanism for the count queries in the case of epsilon delta differential privacy?
No, not possible, because right. So proving that, well, this is a mechanism, and for example, it achieves this reason for all pairs that you're interested in, but proving that this dominates for each pair is, because dominance is on just a pair. Meaning, even if the neighborhood you're looking at was this 3, and you use that mechanism, so on each
You may get
inconsistency on the dominance, meaning
No, but if
is
you
there a
have
way to
one,
use this?
oh, sorry, go ahead.
Is there a way to use this tool to come up with these universally optimal mechanisms?
that connection I could not make so far. So whatever result here and whatever I say here are not comparable directly yet. But I'm just giving you how to use our tool to get some intuition about this. Perhaps there's a way to make the connection precise. We don't have that yet, sir.
Yeah,
So
but
this
the
is
tool does not exclude directly the universal optimality for the designer, because you're
right. This doesn't
applying
exclude it.
simulation under any utility, whereas the utility functions are limited there.
They look at limited utility. Could it be generalized? That I do not have an answer either one way or the other.
Quick question: if you know, for example, if you got a mechanism, a single mechanism, which when restricted to any neighboring pair is optimal, does that imply some kind of global optimality? Because what you said is that you might not always be able to find a single mechanism that's sort of optimal for all pairs, but suppose you have a mechanism which is optimal sort of for all pairs of sense. Does that imply?
No,
some
it doesn't. It doesn't. That's exactly what's happening here. It doesn't imply.
It's not clear.
overall, no. Just, it's not clear, yeah.
So universal is a set of all possible utility functions? Is that how?
No, universality should be said in this context where they look at particular utility and they look at all possible priors and distributions in that context. They prove universal optimality, and that's why I'm using that notion. Other than that, for binary database, meaning there are only two databases, our mechanism is pretty universally optimal in the sense that you can simulate anything else, and that's only two contexts I'm saying universality. Others will be context dependent. Right, good. So what is this good for? Hopefully, I spent quite a bit of time letting you know what all this tool is, and it's quite pretty, but what can we use this for? So one thing that's really nice is we can use it to analyze composition exactly. So composition, yeah, sure.
Go back to your staircase. So basically you're saying you can, for any pair, you can either guarantee epsilon dp or no privacy.
No. This is for over y. So y's are changing. So it's not for any pair. I'll get to that later when I talk about if I have time to go to my last slide. It reappears in my last slide.
Okay.
Let's hope we get fast. Okay. Composition. So composition is the following. You have a database and you're accessing it using multiple mechanisms. And one of the kind of challenging part is that the second query could depend on the output of the first query. So it's an interactive access. And each one is guaranteed, let's say, epsilon I, delta I, differential privacy. And the question is, well, how much privacy is lost? Because you get this bunch of, let's say, k accesses. So you lost a lot of information or privacy, and how much is lost? One very simple guarantee anyone can do is that you can sum these epsilon i's and delta i's, and this output whole thing together, an adversary seeing all the outputs, is guaranteed this particular differential privacy. And that's not difficult to show. And we want to do better. Okay. Right. So we want to get smaller values for epsilon and delta, possibly, that's still guaranteed after k accesses, because you're losing more and more privacy. Large epsilon, large delta is small privacy. Small epsilon, small delta is large privacy. Okay. So the one we're trying to compete against, or we're trying to improve upon, will be the composition theorem by Dork et al. 2010, which shows that, well, let's focus on the cases for the benefit of notation. Let's say everyone is accessing epsilon delta instead of epsilon I delta I, k times, then how much privacy is lost? And they show that, well, in the end, you cannot avoid k delta. That's already lost, because with delta, each time you told the truth. But if you're allowed a little bit of slag, let's say delta tilde, that can be chosen by you, then your epsilon can be much smaller than k epsilon. We're competing against k epsilon, but if you allow a little bit of delta here, then it can be brought down to k epsilon squared. It's roughly epsilon squared, because this is roughly epsilon, plus epsilon square root of k. Okay? So if epsilon is small, k is large, then this is square root of k, much smaller than k. This is epsilon squared, much smaller than epsilon. So this is a big improvement by maybe choosing delta tilde to be 10 to the minus 6. So this is known as a composition theorem that's used everywhere, wherever you have multiple accesses. And this provides, well, this result is on an upper bound on how much privacy is lost, one thing. And this is quite good or tight if we're looking at large k and small epsilon regimes. And the proof is somewhat involved, meaning that there's a lot of algebraic calculations that needs to be done to make sure that the interaction doesn't, and dependencies due to the interaction of the queries doesn't cause any problem. And what we want to do is, given this result, we want to
Previous queries are allowed to depend on the, so next queries are allowed to depend on
previous query outputs. And what we want to do is that, well, we want to use our privacy region to prove a similar composition theorem or understand composition with much tighter, meaning exact results for composition for any k and epsilon. And the proof will be a few lines, given what we know already. So here is how we show or analyze composition. Let's say you are using your favorite mechanism for k access to the data. Each one is epsilon I, delta I, differentially private. That's the only thing you know. Any mechanism, k different mechanisms. And what we know from the converse DPI is that, well, any mechanism, each one, can be replaced by the randomized response, which is the dominant mechanism, plus some statistical transformation. There exists some for each one. Okay. Here, we're only focusing on one neighborhood with two databases.
So I assume they're just missing from the picture, but you're allowed to have dependency arrows going.
Right. So
like
for the right for the just for the presentation, I didn't draw it, but it's everything holds. They are there. I didn't want to draw too many arrows, basically, because you have to have.
Yeah, no, that's fine. I just wanted to check that.
That's true. Yeah, everything is assuming that, but I'm just.
Sorry, related question. Can you choose the epsilon and delta adaptively?
Epsilon and deltas are different, but what you know is that you are accessing with epsilon I delta I differential private mechanism. That information is known.
No, I understand that.
Right? They can
you
be
choose them
different.
adaptively?
Oh, based on what you said before?
The epsilon I is the question.
Oh, so that also is a random variable.
Yeah.
That part I cannot answer right now. I cannot process that information right now. I don't know the answer. Okay. Because.
So the answer is no, there are gaps.
Uh-huh. Thank you.
There you go.
There you go.
Okay, I have a very
Sure.
naive question. So what did you mean by the randomized response as the dominant? See, clearly I didn't understand.
Oh,
So what-
randomized response. What I put here is the one that is the response is that, well, we're just looking at two databases because this is composition. You look at worst case neighborhood. So let's say there's only one neighborhood. This is the one where if you D naught, it's 0. Okay. Delta. And if you're D1, 0. Delta, and this is 1 minus delta. And this achieves the region that you want on the boundary exactly, so anything can be simulated by randomized response plus some transformation that you know exists, but you don't have to specify at this point.
Just jumping ahead for the adaptive, like to handle adaptivity of the mechanisms in this setting.
This will handle whatever.
That only has to, the adaptivity. Only,
Right, it has to come up in the second one.
Second transformation.
Exactly, that's how it
Just push
works
it
out.
into the post-processing,
Exactly,
and that makes the proof.
that proof goes through, yes. So basically what we want to do is that by data processing inequality, this is only more private than just this one. So kind of moving the privacy barrier from here to here. And this one will be just less private, more information is revealed. Let's see how much information is revealed. And you know that whatever you analyze, if you analyze this exactly, can be achieved because there were particular mechanisms on particular database that was achieving exactly the privacy loss that you're analyzing. So it goes both ways. And then at this point is what you need to do is simple. Because if I told someone that this is true and asked for the privacy loss in the end, I think anyone could do it. Basically, you have this k randomized responses, tensor producted, if you will, because at this point they're independent and the output space is just the canonical product of the outputs of each one, and you know the probability distribution, so you just have to analyze it and write it, and that's easy. So how does one do that? Well, one way to view it is that I'm drawing something that's more general than epsilon delta, because everything I said here doesn't have to only be for epsilon delta differential privacy, but for any notion of privacy that you impose as a constraint on the privacy region, if you will. You could have some region like this, or epsilon delta privacy region. Let's say these are the two mechanisms that you're using, and if you have to compose them, just two of them, and ask what the resulting region is, which is actually this one, then how you do it, the computational tool will be the following. For each one, you write the dominant mechanism, which only requires the number of alphabet equal to the number of faces in the polytope. So in this case, 4, in this case, 3. And then you take the Cartesian products. And for this one, if this had n faces and this had n faces, this will have n times n faces at most. Faces. Oh, I give you these two graphs. I want you to draw this graph. That's the composition. Meaning, so you'll have something like this with different slopes and different delta, k of them. You compose two, you get something, and then whatever you get looks like actually this. What you want to do is get this in the end, and on this you want to see how much small polytope or the pentagon can you fit in there by changing epsilon and delta. We'll get there. Okay. So first you want to know what's the resulting region, and you do this, and this can be done automated, it's mechanical, and you get a result like this. And then the resulting composition theorem will be asking, well, if I give you that the resulting region is like this, what's the best epsilon and delta polytope or pentagon you can fit with this one?
I realize that I think the definition of the region is still shaky for me. So the region is that these are, I'm looking over all sets of the probability that something will be accepted.
Right, you from
the
this.
Output will land in the set under distribution 1, distribution 2. That gives me a pair of values, and I plot them.
Right.
Okay, why is everything like below?
Oh, it's symmetric. The other one will be you symmetrize it. I erase the 45 and above just
that
to.
Was exactly what was confusing
Yeah.
me. Good. Check.
Everything is symmetric, exactly. Good. So this gives you a computational tool. And let's say you did this and compose, in this case, epsilon delta differential private mechanism. 1 gives you pentagon. 2 gives you something like this. So you get larger and larger region because you're revealing more and more data. And that shows exactly how composition evolves, or privacy evolves on the composition. For example, I'm just drawing one example of what our analysis can give you. And given this, let's say you did 5-fold composition. If you want a composition theorem, like how it scales with k and epsilon and delta, then you need to, well, you get analytical formula for this one, but it's somewhat combinatorial. So what you do is you try to look at what values of pentagon for epsilon and delta can you fit here. One can do that. It ends up being you apply something like Hefding's, a little bit more than Hefding's, but Chernoff basically, to get something that scales like this. So this will be the this is the Dwork et al. Composition theorem, and this will be looking at the actual composed region, like the dark one here, and trying to fit a pentagon with delta very close to the actual delta, where delta tilde is small. Then you get this. But we give the whole region. And if you just use this upper bound and draw it, then you will get this, which is much larger than the actual composed region. And that's kind of the gap or the improvement that we provide compared to the state-of-the-art composition theorem and our exact theorem. And this is exact theorem. There's a mechanism that achieves it exactly.
Are there other definitions of privacy that you can handle with this? Because this pentagon I understood coming from.
Right, so there's no other definition that people have used that fits this, but you should go the other way. This probably gives you other definitions, like, for example, you can say your privacy region is the intersection of two epsilon 1 delta 1 and epsilon 2 delta 2, which gives you some other shape. And maybe that's you know something about it that is true. Then you can do composition in this way. And this doesn't have to be for just differential privacy. Any region definition would go through the same way.
So Sewoong, if I'm lazy and I just want like a one number view, like I just measure the AUC, right? Flip this and
Yeah, exactly. AUC will be, okay, you'll be integrating it.
Yeah. So, like, is there you quantify the gap? You know, fix it. You know, over epsilon delta.
You want one number.
Yeah. You know, just because I'm lazy.
So that will be related to, so if you're interested in a particular utility, which is a number, depending on your mechanism, that will be corresponding to some function of this region in some cases, but not immediately. So those functions will be typically those that were data processing inequality holds, like KL divergence. And there you can make this precise and use these notions. Right, so we give a computational tool for composing as many as you want, such privacy guarantees that are defined by the region. And we give the composition theorem. And one advertisement is that Sullivan has done a different aspect on this problem where they look at the actual computational complexity of computing the regions that we give. Although you have the formula, but if you wanted to compute it, then it could be as complex as exponential in k. So how do you compute it or approximate it is the problem. So it's sharply hard to compute it exactly, but they give an approximation guarantee. I forgot the ratio. Yeah. Right, so given 1 minute, I'll give you a flavor of where this can be used. So composition is just one place where this can be used. The other thing is differentially private multi-party computation. Has been studied by other people. I'll just tell you the setting and just, I think I should stop. So the setting is that there are n people or k people, let's say. Each one has a data that's private. And someone, an outsider, wants to compute a function over all this data, x1 through xk. And what we can show using our scheme is that, well, each one is using differentially private, let's say epsilon delta mechanism to say something, and this can be interactive. You can wait until someone says something, listen to it, and try to say it. And in all these settings, they will be using some mechanisms that are over time. And this can be, again, broken into randomized response and some transformation where privacy barrier can be moved in. And you can do all this and prove that actually just doing randomized response is optimal. Meaning in this particular setting where you're computing a function over distributed data, differentially private, then you only have, if the data is 1 bit, that's corresponding to, again, having just the one neighborhood. The randomized response, which is non-interactive, is exactly optimal. Can simulate anything, can be simulated by the receiver. And one more thing, in local differential privacy setting, we can use this to, again, show particular results using similar proof technique, but I guess I'm not going to go into the details, and I'll be happy to talk more.